Now that we have the magnetic field from a long straight wire, I want to go back and connect it to what we do with forces. So here's our long wire, and it needs to be a really long wire so that we can use the symmetry. So it's supposed to be a long, uniform, straight wire. And we know that if the magnetic field is in that direction, if the current is in that direction, using our right hand rule, our curling right hand rule, where we put our thumb in the direction of the current and then we curl our hand around, that's R, then we know that our magnetic field, for example, over here is going to be into the page, and over here it's going to be out of the page using our conventions of the X's and dots, and here it will be sort of in that direction, and then there will be our direction of the magnetic field. So if we have a second wire, for example here, and it has current, say, going the other direction, its magnetic field, okay, so this magnetic field here is equal to mu naught I over 2 pi r, and it's going into the page. If I have a magnetic field, for example, with current going the other direction, and I do my right hand rule, then for this one, and if I'm interested in the magnetic field, I'm just going to add the contribution. So in this case, this would also be an X here and a dot here because the current is going down. And so I would add the magnetic field due to the second. So if this is I2, and this is I1, we would have I1, R1, and then magnetic field would be mu naught I2 over 2 pi R2. And so those could add together. And of course, if I change the direction of the current, so I change the direction for this current, I make it go in this direction, so this is I3, then I've got a magnetic field that points in the direction go around like this, like that. There's my magnetic field, and it's coming out of the page right at this spot, and it's going in over here. That this B of 3 could be mu naught I3 2 pi R3. This is R3, and depending on those values, we could actually get the magnetic field canceling out. So the point is we add them, so we add the magnetic fields, but we need to do it as vectors, right? So if they point in the same direction, they add together. If they point in opposite directions, one subtracts from the other, or if they're off at angles, then we're still doing vector components. Okay, what I want to do is now connect this to what we had done earlier about forces. So if we look at this, if we say that I have this wire, so we go back to this I1 and we set up a magnetic field. Ooh, that is not good. We set up a magnetic field like this. So again, this is into the page over here, out of the page over here. And then right at this location, I put a second wire. So we'll put a second wire right there with I2. Then this wire sees a magnetic field due to 1, that's B, is into the page. The magnetic field due to 1 is into the page. This wire 2 now is going to experience a force. Force on 2, remember our force is I, L cross B. So let's figure out which wire we're talking about. So this would be the force on 2 due to the magnetic field it's sitting in. So the magnetic field it's sitting in is 1, is B1, right? So that would be B1, and the length would then be the length of 2 times the current in 2, because that would be our force equation. In other words, the force on this current carrying wire, you can kind of pretend like you've hidden, right, this whatever created it and say, hey, there's a magnetic field that's into the page that this is experiencing, so it's got that force. And so, and of course, because it's a long wire, this magnetic field is of course pointing in that direction all the way along the wire. So we'd use the full length of the wire. So this force that we get from 2, in this case, to figure out the direction of the force, we have our current is up, I cross B, that gives me a force 2, that's this way. Force on 2. And so that would be I2, the length of 2, times the magnetic field due to 1. Again, we just kind of pretend like we don't know what created it, and that gives us the value. These, in this case, would be, this is the magnitude of the force, would be times the sine of the angle between those, which in this case is 90 degrees, and sine of 90 degrees is just 1. So that's a fairly easy calculation. Okay, now, when we have that, we can also say, of course, that there is a force on 1, right? Because 1 also experiences a magnetic field. It experiences a magnetic field due to this second wire, right? This is coming now out of the page, right? It's into the page over there, out of the page here. So that's the direction of magnetic field due to 2. So we kind of go the other direction, right? We hide the stuff on the right and say that this is like that. So the magnetic field is out of the page. I cross B, so the force on 1 is going to be F1, that's due to 2, is equal to the current of 1, the length of 1, cross the magnetic field due to 2. And so when we do that cross product, using our right hand, we get that this is the direction of force 1 into the, towards the other wire. So this force 1, magnitude of force 1 is I1, L1, B2. And so what we get is we get equal and opposite forces, okay? If these are long wires, so L's are the same. And this magnetic field, notice this magnetic field due to 1 is mu naught I1 over 2 pi r, where this is the distance, right? R is our distance. Sorry, I'll make it a little r. Or, yeah, I'll make it a little r, so it doesn't confuse with the radius of a loop. And then over here, this becomes I2, mu naught I2 over 2 pi r, or the force that 1 feels, which is attractive, is equal to I1, I2 times the length. They both have long, super long. So L's tending towards infinity, which is kind of problematic. We don't want to have infinite forces. So we usually talk about force per length is equal to 2 pi r. And then force for number 2 would be mu naught I1, I2L over 2 pi r. Or the way we usually talk about this, because this runs into some problems with infinity, if we have an infinitely long L, then we've got an infinitely big force. So we talk about force per length on the wire is mu naught I1, I2 over 2 pi r, and force 2 over L, the magnitude of it, is mu naught I1, I2 over 2 pi r. So these are, in fact, actually the same value, and they are going to be equal but in opposite directions, consistent with Newton's third law, which is kind of a satisfying relationship. So this is when the currents are in the same direction. Notice that if we have a situation where we set this up, so this is the same thing we had before, its magnetic field looks like that. So it's into the page there. We put our second wire in. This time we put our second wire the other direction. Then we have our I is in that direction. Our magnetic field is into the page. So our L, our force, which is IL cross B, right, on 2, this is I2, would be the length is in this direction. That would be the direction of L, because it's always in the direction of I, and that gives us a force that's like this. So it's a repulsive force in this case. So if you have wires where the current is traveling in the same direction, it's attractive. It's called pinching the wires of the current. Actually, when you run current in wires like this, they can pinch together. They tighten, they get closer together because they're drawn in together. But if you have wires with forces in opposite directions, then they repel each other due to this magnetic force.